In this podcast, we're going to talk about half-life, and this will be for C. Alright, first let's talk about what half-life is defined as in kinetics. Basically, it's the time required for 1/2 of a reactant to react. So here you see we started with 150, and so the first half-life is going to be here, which is 75, okay? So that's a little over, probably about 13,000 seconds. All right, there are different equations that we use. Typically, we've been using the first order half-life equations because we found that the majority of half-life, radioactive half-life, occurs on a first order kinetics basis. But there are half-life equations for second order and zero order. Second order, the equation of T1/2 equals 1 over K natural log AO. And then for zero order, we see that the equation is T1/2 equals AO over 2K. Alright, so here we have an example problem. A first order chemical has a half-life of 8 minutes. How long will it take for 93.75% of this chemical to disappear as it is transformed into products? Alright, first off, let's go ahead and write the first order half-life equations. So we know T1/2 is equal to natural log of 2 over K, okay, because this is first order. And then our other equation is negative KT equals natural log, well, that really should be I just messed that one all up. All right, natural log of A over AO. Gotta love this little pen today. It's like dragging really bad. Okay, so how long will it take for 93.7% to disappear? So if 93.75% has disappeared, we'll really only have, let's see, 100 minus 93.75. We will only have 6.25% left. So that's going to be our A over here. So 6.25%, which we'll have to get into decimal form later, will really be our A over AO. All right, so first let's go deal with finding K, because we know the half-life is 8 minutes. So we have 8 equals natural log of 2, which is 0.693 over K. All right, we cross multiply that K up, and then we divide by 8 on both sides to get K by itself. So we end up with 0.693 divided by 8 is equal to K. So our K is 0.0866. Okay? All right, so now we can go plug that in over here because we're looking for time. Okay, so we have negative 0.0866 times time is equal to the natural log of only having 6.25% left because we want this much of it gone. Okay, so we're assuming our original amount is 100 and we only have 6.25 left. Okay, so we need to get that out of the decimal form or the fraction form and into decimal. Oh crap, I didn't move it too many places. Should have only been right there. Okay, so 0.0625. All right, so we need to natural log that side first. So I'm going to plug in natural log of 0.0625, and you get negative 2.77. Okay, and that is equal to negative 0.0866 t, and we're trying to find out how much time, so we're going to put t by itself. Alright, so there we go. And then we have negative 2.77 divided by the negative 0.0866, and we get 32. So that's 32 minutes, and you're only going to have 6.25% left, which means 93.75 of it has disappeared and turned into products. Okay? All right, this next example says that we have a reaction 2x going to y, which follows second order kinetics with a half-life of 4 minutes. All right, so I'm going to have to back scroll because I definitely do not know this one by heart. So we've got 1 over k AO. Okay, and that equals T1 half. Okay? All right, so we have our half-life, which is 4 minutes, and wants to know the value of K. Okay, and we also have this AO to deal with. AO is the initial concentration, which is 3.6 molar. Okay, so we're going to have 1 over K times 3.6 equals 4. Okay, so cross multiply that 3.6 up. So 4 times 3.6. Okay, that gives us 14.4, which equals 1 over K. All right, and then basically now we just need to inverse both sides. So we really want to know what 1 over 14.4 is so that we can get the value of K. Okay, so when you do that, you get K equals 0.0694. Okay, there's our K. And so that's A, and now it wants to know what is the concentration after 15 minutes. So now we're going to have to employ our other equation that we use for half-life. So we have our T1 half, and then we have our negative KT equals natural log of A over AO. Okay, and we just used that equation on the previous problem. So we got 0.0694 times time, which is 15 minutes, 15 equals natural log. It wants to know the concentration, so we're looking for A, and our original concentration is 3.6. Okay? All right, so first we can deal with this side. So we've got the negative 0.0694 times 15. So that is negative 1.041. All right, now we got to deal with this natural log. So we're going to E both sides. So this to the E, and then when you E this one, that cancels out. And you get A over 3.6. Okay, so if we do E to the negative 1.041, we get 0.353. Running out of room, 0.353, and that's equal to A over 3.6. Cross multiply the 3.6 up, and that'll give you A. So A is 1.27. And the units are at molarity.